Hello and welcome to our demonstration of 2UDFs and beyond. In our work we explain how to fully decompose a data processor and which benefits it can bring. We implemented the proposed changes in our existing Yoda data processor. The goal of decomposing Yoda is to support all kinds of user-defined modules. Imagine an e-commerce platform that stores thousands of customer reviews. The business needs to filter these reviews and perform sentiment analysis to measure product satisfaction, identify improvement areas, and enhance overall customer experience. However, the vast amount of semi-structured review data poses challenges in terms of processing efficiency, analysis accuracy, and the integration of custom analysis pipelines. Traditionally, sentiment analysis demands custom data processing code in a programming language of choice, like Python. This code needs to handle data import, pre-processing, transformation, and exporting, which adds complexity and may not take advantage of existing systems. The process can become cumbersome, resource-intensive, and prone to errors. By modularizing databases and data processors, like our Yoda system, and supporting user-defined modules, one can benefit from the existing ecosystem of libraries while replacing complex, custom-developed data pipelines with one easy-to-use data processor with a simple query language. Extending a data processor to allow users to define their own modules and functions is a powerful and flexible approach that can bring several benefits to the system. Allowing users to define their own modules and functions empowers them to tailor the systems to their specific needs. This leads to a more personalized and efficient experience, as users can create functionalities that directly address their unique use cases. Data processors are often used to manipulate and transform data in various ways. By enabling users to create custom modules and functions, you're giving them the freedom to implement complex transformations and operations that might not be natively supported by the processor. This flexibility can make the tool more adaptable to a wider range of tasks. Users with specific domain knowledge can create domain-specific functions that abstract away complex operations and make them more intuitive for others in the same domain. This enables domain experts to communicate and work effectively with the data processor without needing deep technical knowledge. By being able to share modules with each other, a collaborative environment is created where users can benefit from each other's expertise. This can lead to the creation of a library of reusable components that extend the functionality of the system even further. Also, opening up the system to user-defined modules encourages innovation. Users might come up with creative solutions to problems that the core development team might not have considered. This can lead to unexpected and valuable enhancement to the processor's capabilities. Requirements and use cases can evolve over time. By offering a way for users to extend the processor functionality, the system becomes more adaptable to changing needs without requiring major updates from the development team. As initial supported language, we chose Python. Python is one of the most popular and widely used programming languages. Many users, including both developers and non-developers, are already familiar with Python or can quickly learn its syntax. This familiarity can lower the entry barrier for users looking to extend the system's functionality. Python also has an extensive ecosystem of libraries and frameworks that cover a wide range of functionalities, from data manipulation and analysis to machine learning and web development. By allowing users to leverage Python, you tap into this rich ecosystem and give them access to powerful tools and resources. This extensive ecosystem, coupled with the language's versatility, allows users to implement a broad spectrum of functionalities. They can perform data transformations, calculations, string manipulations, and even interact with external APIs or databases, depending on their needs. By using this modularization, the system can become part of a larger ecosystem or interact with other tools. Python offers a plethora of libraries and frameworks for API communication, web services, and more, making it easier to bridge the gap between different components and building a custom data processing pipeline. Python is used in a wide range of fields, from software development to data science, scientific research, automation, and more. Allowing users to utilize Python means that individuals from various backgrounds and skill sets can contribute to extending the system's capabilities. As mentioned before, we have applied this modularization to our Yoda processor. Users can now add user-defined modules and functions to the system, which can then be used in the data processing pipeline. These modules can be used to add new import capabilities, such as reading data from a specific file format, different system or API. Similarly, users can also add new export capabilities, user-defined functions to extend the functionality of the language on a tuple basis, user-defined aggregations to extend the functionality of the language on a group basis, and user-defined indices to improve query performance for specific use cases. Now that we have talked about the what and why, let's see how it works in practice. Here we see the web interface of Yoda. As we can see, we already loaded a small simplified dataset of tweets, which we'll use in a second. It consists only of the tweet text and some geo-coordinates of where the tweet has been sent from. The currently loaded user-defined modules can be seen here. As we can see, no modules are loaded. A new module can be uploaded by simply pressing this button. We extended Yoda to support user-defined modules that add query functions, aggregation functions, new import and export functionalities, and even indices. The module framework is completely language agnostic, but we currently only implemented support for Python modules. The goal is to allow the user to easily modify any part of the system while keeping the fast performance of Yoda. In the future, we also want to support user-defined query scheduling and even extending the structure of the query language itself. For now, let's get started by adding the following Python module. To add a query function, we only have to specify the number of arguments and the function itself in the method named getValue. Yoda passes all arguments onto the Python script, translate the result back into JSON for further use in the query. This module uses a trained model to infer the sentiment of a given text. Using less than 30 lines of Python code, we can now extend Yoda with previously non-existing AI capabilities. We can now see the module here in the overview, where its function name, type, and language is shown. If we want to remove it again, we can do so here. We'll now test this module by inferring the sentiment of all tweets. Yoda is designed to be very fast by executing as much as possible in parallel and in memory. As we saw, adding new query functions is very easy, and thanks to the Yoda architecture, executing this query is even faster than getting the same result in native Python. As we can see, we now have the set of tweets with an added sentiment. In the next example, we'll now use this module to predict the language of all tweets and add it to the dataset. Again, adding these capabilities only took less than 30 lines of code. The inferred language is now also part of our dataset. Yoda also supports adding aggregation functions. As aggregations are performed in parallel and intermediate results are required, implementing an aggregation function is a little bit more involved. We again have to specify the number of arguments, initialize a state that will be used to locally compute a partial aggregation in each thread, the actual aggregate method, which takes one tuple and adds it to the state, a merge function that merges two partial results, and a finalize function that translates the merged state into the final representation. We'll use this module to calculate the bounding box of all locations of our previous set of tweets where the sentiment was positive. We also group the aggregation by the inferred language. If we wanted to manually compute the bounding box, the query would have to be more complex and involve 4 separate aggregations. Here we see all bounding boxes grouped by the language. Yoda by itself only supports JSON input and output, but by decomposing the input and output functionality, the user can now also support custom data types. Writing an export module only requires an initialization function, which given a configuration string sets up all required classes and connections. Then for every document to be exported, the setNext function is called. Finally, after all documents have been processed, the finalize method is called, where any connections can be closed. This module enables Yoda to write to a CSV file using only 18 lines of code. In this query, we'll use our module to export the previous result. And we can see the resulting file here. This is a very powerful extension, as it also allows us to integrate Yoda with other tools into a larger data science pipeline. This module, for example, adds support for importing data from a Postgres table. By decomposing Yoda, it is now also possible to use it as a very powerful research tool, as new indices can be rapidly prototyped in Python and evaluated for usability and performance. This code, for example, is a very simple query cache that caches the results of previous filter queries and can quickly recall them. After importing it, Yoda will automatically use this index when suitable. Thank you for listening, and we hope you liked our demonstration.